Hello students, with me, Miss Yessica. Do you still remember what you have learned last week? Yes, last week we have learned about blood, so today we are going to learn about the hemoglobin. Hemoglobin. I think all of you know that a major role of the cardiovascular system is to transport oxygen from the gas exchange surfaces of the alveoli in the lungs to the tissues all over the body. Body cells need a constant supply of oxygen in order to be able to carry out the aerobic respiration. Oxygen is transported around the body inside the red blood cells in combination with the protein hemoglobin. So hemoglobin, it is a red pigment and it's present in the red blood cells, and the hemoglobin is made out of the iron and the proteins. So hemoglobin structures. I have mentioned in the previous slide that the hemoglobin is made up of the iron and protein. So the iron containing the pigment called the heme attached with the protein's globin. Globin made up of 4 polypeptide chains, consists of 2 alpha chains and 2 beta chains. 4 units of heme attached to 1 unit of globin. So it means that 1 hemoglobin molecules contains 4 iron atoms which carry 4 molecules of oxygen. And for the reactions you can see on the slide. Function of hemoglobin. Hemoglobin used to transport oxygen to tissues. It also used to transport the carbon dioxide to the lungs and also to maintain the acid-base balance, or it acts as the buffer. The hemoglobin dissociation curve. A molecule whose function is to transport oxygen from one part of the body to another must be able not only to pick up the oxygen at the lungs, but also to release oxygen within respiring tissues. Hemoglobin performs this task superbly. To investigate how hemoglobin behaves, samples are extracted from blood and exposed to different concentrations or partial pressures of oxygen. The amount of oxygen which combines with each sample of hemoglobin is then measured. The maximum amount of the oxygen with which a sample can possibly combine is given a value of 100%. A sample of hemoglobin which was combined with this maximum amount of oxygen is said to be saturated. The amount of oxygen with which identical samples of hemoglobin combine at lower oxygen partial pressures are then expressed as a percentage of this maximum value. The table in the slide shows a series of the results for search and investigation. The percentage saturation of each sample can be plotted against the partial pressure of oxygen to obtain the curve shown in this slide. This is known as the dissociation curve. The curve shows that at low partial pressures of oxygen, the percentage saturation of hemoglobin is very low. It means that the hemoglobin is combined with only a very little oxygen. At high partial pressures of oxygen, the percentage saturation of hemoglobin is very high, or it means that it's combined with a large amount of oxygen. Consider the hemoglobin within a red blood cells in the capillary in the lungs. Here, where the partial pressure of oxygen is high, this hemoglobin will be around 95 to 97% saturated with the oxygen. It means that almost every hemoglobin molecule will be combined with its full complement of 8 oxygen atoms. In an actively respiring muscles, on the other hand, where the partial pressure of oxygen is low, the hemoglobin will be about 20 to 25% saturated with the oxygen. So it means that the hemoglobin is carrying only a quarter of the oxygen which it is capable of carrying. This means that the hemoglobin coming from the lungs carries a lot of oxygen. As it reaches the muscle, it releases around 3/4 of it. This released oxygen diffuses out of the red blood cells and into the muscles where it can be used in the respiration. The shape of the hemoglobin dissociation curve can be explained by the behavior of a hemoglobin molecule as it combines with or loses oxygen molecules. Oxygen molecules combine with the iron atoms in the heme groups of a hemoglobin molecule. We will remember that each hemoglobin molecule has 4 heme groups. When an oxygen molecule combines with one heme group, the whole hemoglobin molecule is slightly distorted. This distortion makes it easier for the second oxygen molecule to combine with the second heme group. This is turn make it easier for the third oxygen molecule to combine with the third heme group. It is then still easier for the fourth and the final oxygen molecule to combine. The shape of the hemoglobin dissociation curve reflects the way that the oxygen atoms combine with the hemoglobin molecules. Up to an oxygen partial pressure of around 2 kilopascal, or on average only one oxygen molecule is combined with each hemoglobin molecule. Once this oxygen molecule is combined, however, it becomes successfully easier for the second and the third oxygen molecule to combine. So the curve rises very steeply. Over this part of the curve, a small change in the partial pressure of oxygens causes a very large change in the amount of the oxygens which is carried by the hemoglobin. The behavior of hemoglobin is picking up oxygen at the lungs and readily releasing it when in the conditions of low oxygen partial pressure is exactly what is needed. But in fact, it is even better at this than this shown by the dissociation curve in the previous slide. This is because the amount of the oxygens the hemoglobin carries is affected not only by the partial pressure of the oxygen, but also by the partial pressure of carbon dioxide. Carbon dioxide is continually produced by the respiring cells, like from the metabolisms. It diffuses from the cells and into the blood plasma, from where some of it diffuses into the red blood cells. In the cytoplasms of the red blood cells, there is an enzyme, carbonic anhydrase, that catalyzes the following reactions. Okay, you can see that this enzyme, the carbonic anhydrase, it catalyzes the reaction of the carbon dioxide with the water to form the carbonic acid. The carbonic acid dissociates to produce the hydrogen ion and hydrogen carbonate ion. Hemoglobin readily combines with the hydrogen ions, forming the hemoglobinic acid, or HHV. In so doing, it releases the oxygens which it is carrying. The net result of these two reactions are, firstly, the hemoglobin moves up the hydrogen ions which are formed when carbon dioxide dissolves and dissociates. A high concentration of hydrogen ions means a low pH. If the hydrogen ions were left in the solution, the blood will be very acidic. By removing the hydrogen ions from solution, hemoglobin helps to maintain the pH of the blood close to natural. It is acting as a buffer, like I have mentioned in the very beginning of slide. The presence of the high partial pressure of carbon dioxide causes the hemoglobin to release oxygen. This is called the Bohr effect. After Christian Bohr, who discovered it in 1904. It is exactly what is needed. High concentrations of carbon dioxide are found in actively respiring tissues, which need oxygens. These high carbon dioxide concentrations cause the hemoglobin to release its oxygens even more readily than it will be otherwise do. If a dissociation curve is drawn for hemoglobin at the high partial pressures of carbon dioxide, it looks like the lower curve shown on the previous graph. At each partial pressure of the oxygens, the hemoglobin is less saturated than it will be at low partial pressures of carbon dioxide. The curve therefore lies below and to be the right of the normal curve. So this is the dissociation curves for hemoglobin at two different partial pressures of carbon dioxide. The shift of the curve to the right when the hemoglobin is exposed to the higher carbon dioxide concentration is called the Bohr effect. The description of the Bohr effect explains one way in which carbon dioxide is carried in the blood. One product of the dissociation of the dissolved carbon dioxide is the hydrogen carbonate ions. These are initially formed in the cytoplasms of the red blood cell because this is where the enzyme carbonic anhydrase is found. Most of the hydrogen carbon ions then diffuse out of the red blood cells into the blood plasma, where they are carried in solutions. About 85% of carbon dioxide transported by the blood is carried in this way. Some carbon dioxide, however, does not dissociate but remains as carbon dioxide molecules. Some of these simply dissolve in the blood plasma. About 5% of the total is carried in this form. Other carbon dioxide molecules diffuse into the red blood cells, but instead of undergoing the reactions catalyzed by the carbonic anhydrase, combine directly with the terminal amine group of some of the hemoglobin molecules. The compound form is called the carbaminohemoglobin. About 10% of the carbon dioxide is carried in this way. When blood reaches the lungs, the reaction described go into reverse. The relatively low concentration of the carbon dioxide in the alveoli compared with that in the blood causes the carbon dioxide to diffuse from the blood into the air in the alveoli, stimulating the carbon dioxide of carbaminohemoglobin to leave the red blood cells, and the hydrogen carbonate and hydrogen ions to recombine to form the carbon dioxide molecules once more. This leaves the hemoglobin molecules free to combine with oxygens, ready to begin another circuits of the body. Next, we are going to discuss about the problems with the oxygen's transport. The first one is the carbon monoxide. Despite its almost perfect structures as an oxygen transporting molecule, hemoglobin does have one property which can prove very dangerous. It combines very readily and almost irreversibly with carbon monoxide. Carbon monoxide is formed when a carbon-containing compound burns incompletely. Exhaust fumes from cars contain significant amounts of carbon monoxide, as does cigarette smoke. When such fumes are inhaled, the carbon monoxide readily diffuses across the walls of the alveoli into the blood and into the red blood cells. Here, it combines with the heme groups in the hemoglobin molecules, forming the carboxyhemoglobin. Hemoglobin combines with the carbon monoxide 250 times more readily than it does with the oxygens. Thus, even if the concentration of the carbon dioxide in the air is much lower than the concentration of the oxygens, a high proportion of the hemoglobin will combine with the carbon monoxide first. Moreover, the carboxyhemoglobin is a very stable compound. The carbon monoxide remains combined with the hemoglobin for a very long time. The result of this, that is, even relatively low concentration of carbon monoxide, as low as 0.1% of the air, can cause the death of asphyxiation. Treatment of carbon monoxide poisoning involves administration of a mixture of pure oxygens and carbon dioxide. High concentration of oxygens to favor the combination of the hemoglobin with oxygen rather than the carbon monoxide. And carbon dioxide is used to stimulate an increase in the breathing rate. Cigarette smoke contains up to 5% of carbon monoxide. Okay, so please don't smoke, students. If you breathe any pure cigarette smoke for any length of time, you will die of asphyxiation. As it is, even smokers who inhale also breathe in some normal air, diluting the carbon monoxide level in their lungs. Nevertheless, around 5% of hemoglobin in a regular smoker's blood is permanently combined with the carbon monoxide. Wow. This considerably reduces its oxygen carrying capacity. Second is the high altitude. We obtain our oxygen from the air around us. At the sea level, the partial pressure of the oxygen in the atmosphere is just over 20 kilopascal, and the partial pressure of oxygen in the alveolus in the lungs is about 13 kilopascal. So if you look at the oxygen dissociation curve for the hemoglobin in the previous slide, you can see that at this partial pressure of the oxygen, hemoglobin is almost completely saturated with oxygen. If, however, a person climbs up a mountain to a height of 6,500 meters, then the air pressure is much less. The partial pressure of oxygen in the air is only about 10 kilopascal, and in the lungs about 5.3 kilopascal. You can see from the previous slide that this means that the hemoglobin will become only about 70% saturated in the lungs. Less oxygen will be carried around the body, and the person may begin to feel breathless and ill. If someone travels quickly over a period of just a few days from the sea level to a very high altitude, the body does not have enough time to adjust to this drop in oxygen availability, and the person may suffer from the altitude sickness. The symptoms of the altitude sickness frequently begin with an increase in the rate and the depth of breathing, and a general feeling of dizziness and weakness. The symptoms can be easily reversed by going down to a lower altitude. Some people, however, can quickly become very ill indeed. The arterioles in their brain dilate, increasing the amount of the blood flowing into the capillaries, so that the fluid begins to leak from the capillaries into the brain tissues. This can cause the disorientation. Fluid may also leak into the lungs, preventing them from functioning properly. Acute altitude sickness can be fatal, and the person suffering from it must be brought down to the low altitude immediately or given an oxygen. However, if the body is given plenty of time to adapt, then most of people can cope well at the altitudes up to at least 5,000 meters. In 1979, two mountaineers climbed the Mount Everest without the oxygen equipment, returning safely despite experiencing the hallucination and feelings of euphoria at the summit. As the body gradually acclimatizes to a high altitude, a number of changes take place. Perhaps the most significant of this is that the number of the red blood cell increases, whereas the red blood cells normally make up about 40 to 50% of the blood, but after a few months at the high altitude, this rises to as much as 50 to 70%. However, this does take a long time to happen, and there is almost no change in the number of red blood cells for at least 2 or 3 weeks at high altitude. People who live permanently at high altitudes, such as in the Andes or the Himalayas, shows a number of adaptations to their low oxygen environment. It seems that they are not genetically different from people who live in low altitudes, but rather that they are exposed to the low oxygen partial pressures from the birth encourages the development of these adaptations from at early age. They often have especially the broad chest, providing a larger lung capacities than normal. The heart is often larger than in the persons who live in the low altitude, especially the right side, which pumps the blood to the lungs. They also have more hemoglobin in their blood than usual, so increasing the efficiency of the oxygen transport from the lungs to the tissues. So that's all for today. Thank you for your attention and goodbye.